Welcome to one of the video on how to draw the CMOS layout. So let us start with a very simple circuit, that is a basic circuit inverter. So inverter has got one PMOS transistor and one NMOS transistor. It has to be realized on a same substrate. So let us consider a P substrate, then let us assume that the background white paper is P substrate. So I want to have an NMOS transistor as well as a PMOS transistor fabricated. First of all, let me have a well created which is called as N well. So I am defining a region where I am going to have the N well. This is N well. So in this N well, I am going to have N diffusion. Okay, let me have in this N well, I'll have the P diffusion to realize PMOS transistor, and in this substrate N substrate, let me have the N diffusion to have the NMOS transistor realized, and I'm going to run a poly across this to realize the gate structure. So this is the poly that is realized, that is used to realize the gate structure. Now, since we have already identified which is gate, drain and source, and then let me also write one VDD and VSS. So I'm just trying to use the conventional colors that are used for the layouts. So metal will be blue in color. I'm using the same color. So now let us try to connect the source and drains to. This is VSS. So if you name it as source, drain, this is drain, source, and this is connected to this metal. There is a contact cut made here, and similarly there is more. This is going to establish this connection. This connection is done here. Then let me short this drain and this drain, which is exactly here. Let me short these two. This is again contact cut, and of course this is the input, and this becomes the output. So this is if I name it as M1, M2, so this is M1 realized here, this is M2 realized here, this is input, this is output. So this is how we can able to realize an inverter layout. So let us go to Microwind and then try to realize the same thing. And as I said, this is the background substrate, which is N substrate. Let me have a N well. So I'm just defining some region. This is N well. I'm going to have a N plus diffusion in this. Okay, I'll have a P plus diffusion somewhere here, and I'll have a polysilicon crossing both of them, which we realize. Sorry, that was not polysilicon. Let me just undo that. Let me just take out this and then remove this. Okay, let me take this my polysilicon, cross it over this, and you can see this is one transistor and not this is PMOS transistor to realize. Okay, whether this is a transistor or not, what you can do is you can do a one big cut here. You can see this is what is the source bar drain. This is again drain bar source. This is gate oxide, and this is the polysilicon. So this is exactly an NMOS transistor. If you want to see the PMOS transistor, you can have a contact cut here. You can see this is N well. So there is a P plus diffusion, and of course this is your gate structure, and of course you can see there is a 2 nanometer gate oxide. So this is what is realization of NMOS and PMOS transistor. Next, if you are naming this as source and drain and source and drain, let me have one metal 1 here as VDD and this as VSS. You can see this is analogous to that of my circuit, what I am drawn here. Then I need to have a contact cut here. So what I'll do is let me just extend the same metal over here, and you can see you need to make it connect here. So that is done using, you see here there is connect layers. If you make this connect layers, actually the diffusion and the metals are connected to a via that you can realize here. You can make a contact cut, then see this how it is. You can see this is you can just realize there are so many layers where you can able to put the metal. Since I put M1, which is metal in layer 1, is connected to one of the diffusion of MOS transistor, which we name it as source. Source is now connected to this metal, which is exactly this connection. The source is connected to VSS, this source is connected to VSS, this source is connected to VSS. Then similarly, this source is connected to VDD, so this source should be connected to VDD. So what I want is now, so let me take this, of course metal is already taken, let me take this and connect it to this. Suppose if you don't make any contact cut, the connection is not established. Suppose if I just make a contact cut here, you can see there is a metal running and this P diffusion is there, but there is no contact cut, there is no connection now. So that will be created only when you make a contact cut. So you can just, let me show you that. Okay, now let me connect layers. Only when I do this connect layers, then only it will get connected. So you can see now there was now we can see, can you see this now? So this is now established. So this connection was not there when you didn't make that contact cut. So that's why it's very important if you want to make a connection from diffusion to metal. So it is a must to have a contact cut. Of course this is drain, so that also need to be connected through metal, and you need to make a connection. So connect layers, then connect layers. So this has established actually this circuit diagram. So whatever that we have written here, the background is P substrate, and you have a N well, you put a P diffusion, this is N diffusion, there is a polysilicon running here, this is metal, this is ground, and now we can able to apply the input voltage and we can see what is the output. So what I'll do is, let me do that. So let me connect that VDD supply to this, and VDD should be connected to N well also, we'll discuss that later. And there is a ground connected to this, it's done here now. So let me see the output over here. Okay, this is, let me name it as output, and let me apply the input here. So let me apply input voltage which is a clock like thing. This is my input voltage of, maybe you can have a lower frequency, a sine. Now it is, a clock is applied. At the output you have to see an inverted clock. Let me run this. If you can see now, it's exactly the let me just run it for, now you can see this is the input voltage. Let me just reset, and then I can see this is the input voltage which is 0. When the input is 0, output is 1. When the output is 1, when the input is 1, output is 0. Of course you can see it is taking some time, the fall time and rise times. So this we'll discuss in the coming classes. Okay, this is what an inverter looks like. So this is the layout of CMOS inverter. We started with drawing a N well. N well is used to realize PMOS transistor, and since the substrate is P substrate, I have N diffusion to realize NMOS transistor, and of course you have a common gate to short the gate of PMOS transistor and NMOS transistor, and this is supply rail, VDD and VSS, and this is a drain connection, this is input, and these are the output. Let us quickly do it for the NAND gate. So for the NAND gate it looks something like this. So let me just do it for NAND gate. So as we know that NAND gate has got two pull down transistors in series and two pull up transistors in parallel. So this is VDD, VSS, this is A, this is B, this is A, this is B, and this your Y is equal to AB whole bar. So we know that there are two transistors. You can actually draw the Euler's path here. So this is Euler's path, which is actually starting from a point and going back to the same point. And you can see this is if you start naming the source and drains, this is source, drain, drain, source. This is actually source, drain, source, drain. So now the input configuration is first it is A and then B, and you have an N well. So this is my N well here, and you have a P plus diffusion, and you have a N diffusion here, again N plus diffusion. There's a poly running here. Okay, let me run the poly. There is a poly running here, and there is one more poly here. So this poly indicates the gate structure. So as the gate naming is A and B, let us name this as A and B. Since we are starting from this here, let me name this as source, drain, drain, source. And since this is A structure, this is source, drain, sorry, this is again source and drain. No, this is, sorry, this is actually drain, source, sorry for that, because source of the NMOS transistor is always at lower potential. So this is source, drain, sorry, this is drain, source, drain, source. Is that fine? This is drain, it is this, source is this, then again drain, and this is source. This is source. I think it's fine. So now we know that let us have the metal lines. So this is one metal line, this is the other metal line. So since source and source are shorted here, let me short this source, let it extend here, let it extend here. This is source and source shorted, and then this source, this is B transistor, only that particular source is shorted with done, and then this is this drain. This drain is going to this drain again through metal. This is shorted here, this is shorted, these are the contact cuts. So these are all this is the layout. Of course, this is the final output. Y is equal to AB whole bar. Okay, let us realize the same thing in this is actually VDD VSS. VDD VSS. If both the inputs are 1, then only you are going to get a 0. So otherwise the output is always high. Okay, let me take a new one. Okay, let me have the anvil. This is my anvil. Okay, this is my N diffusion. This is my P diffusion. I'll have two polysilicons crossing corresponding to two inputs. One input, second input. You can, okay, take this metal one. This is VDD, this is VSS. Maybe you can have this as a reference so that you can able to draw it as per that. Then what we have is, okay, the same metal is connected here. Metal is, now you can see, since it's not what you can do is that you can select that, or you can extend this in P diffusion to slightly this fine. And then I need to have this metal connected to this is what is my output, and then and these are my contact pads. Okay, here you connect the layer, no connection, sorry, this is connect the layer, then connect the layer here, connect the layers, then apply VDD to this, VDD to envel, ground to this, and you can apply maybe you can apply okay, a clock 1 to this, and clock 2 to this one, because the frequency will be automatically halved, so that you need not have to worry. It is assigned now. So this is my output. Where I'm going to see this. Take this I. See the output now. It is now the output. Now you can say run. If I just do it for smaller time, you can see now. Whenever both the inputs are 1 1, you can see output 0. For other cases, output is always high. Whether it is 1 0 0 0 0 1, output is high. Only when the inputs are 1 1, output is 0. So this way, you can able to easily realize any given logic using by drawing the layout. Let us draw one more slightly critical layout. Maybe let me just take that. Y is equal to A plus BC into D, because Y bar is equal to. So realization of this is A, BC, and then D. This is our pull down transistor. This is A, B, C, D. Similarly, you can have, this is my D, and these two are in series. It will actually become parallel here. This is A. Then you can think of these two are in actually series, they will become parallel, and then that parallel combination is now in series with this AB. Okay, let me just put it here. I hope that this is fine. This is BC. Correct. This is what we have now. Now I can just take this as so we can start from this. How do I do this? So because I need to write, okay, this is VDD, this is VSS. So what you can do is, okay, you can start from here. This is drain DABC. This is DABC. This pattern. You can see now this is started from D, then A, then B, then C. This is DABC. Ensure that you have the same pattern here. This is DABC. Now let me start drawing this is what source, drain, source, drain, source, source, drain. Here it is now drain, source, source, drain, source, drain. If I do it for the pull down network, pull down is green NMOS transistor and diffusion. This is brown with the well, and write the well also here, and I will write the polysilicon. This is D, A, B, C. This is the ABC. The input patterns, let me write it as input D, A, B, C. So if you can see now, I can start writing. So since I started from here, this is source, drain, source, drain, drain, source, drain and source. This is drain and source of C transistor. Start from this. So I started with the source, drain, drain, source, drain, source, drain. So this is done now. So let me have the VDD and ground. To the ground only one terminal is there, that is source of D. Only this is grounded here. Because this is D, this is source, and this is connected here. So I need to short this source of A, drain of this, and then this. So you can see this source of C has this connection is not there. Source of this source of C has to be connected to drain of D and source of A, which is this. So I need to have a connection from this to this. This will actually establish this connection. This connection is, because path is not closed here, so this has to be done here. So this is that connection. Then final output is there in this drain. So since this is your output point, since you already have a metal one, so you may have to use other metal too. So you may have to use, okay, let us do that later. Let me complete this. And how many terminals are going to source? So, sorry, VDD. So this is one which is going to VDD here. And then this source and this source. That is source and source of this. Done. And then drain and source of this. Drain of C should be shorted with drain source of E and E. This is, it should be get shorted. Then okay, this is the drain point, which is A and D. This is A and D. This is that output point. This output should be shorted with this drain. So this point. Okay, this is my actually this is the output point. There is no output. Okay, let us. I hope this is clear. So we have this drain of A transistor A and D, which is A and D drain, and A and D of drain of A and B. This is A and B. This is drain. This and this is a common point for the output only. Okay, let us go back to that. Let me just. Okay, let me close this. Take a new one. Yes. Okay, let us keep both of them aside. Let me put this down here. Now let me have the bell. Bell is here. Let me have a bell in diffusion because I need to have an empty. This is pre-diffusion done. Then let me have the polysilicon, 5 polysilicons because I got 5 gates. 1, 2, 3, 4, then 5. Let me slightly extend this. Let me extend this also. And let me have a polysilicon, sorry, metal running here for VDD, VSS, and there should be a metal here for this, and there is one metal going from this is done, this connection is done, this is done. So let me connect this to this, and then one more metal should come down here, and then from this is it fine? Actually we had only 4, no? I don't know why did I make it 5. So let me take out this. So I don't have 5 polysilicon, I have only 4. Let me take out this. I'll pick out that, fine. So let me extend this. Okay, let me draw the metal. Okay, this is done. This is what is this, and this is my final output. Output is this. You can see built. Since I have metal 1 here, so I cannot cross to this point. Like we use metal 2, and then show this. Let me show you what is the importance of metal 1, metal 2 here. You can see now, since I'm just going like this, it's actually there in a different layer. So let me show you that. Okay, how it looks like. You can see now. This is in metal 1, metal 2. You can see this is metal 2, this is metal 1. Even though I'm just crossing that, since it is there in different layers, they are not shorted. They are not shorted. Suppose if I use the same metal, this would have got shorted here. And okay, now I can make the connects. I can have one connect. This is the connect. This is another connect. This is another connect. So I'm just making the connection of all metal to diffusions. Connect layers, connect layer. This also I'm supposed to connect the layer. This also I should connect the layer. If I see the output here, this is my output. This is okay. Let me connect that to VDD and grounds. Again VDD to point diffusion. Okay, and well, this is ground here. So as per this, okay, your output will be 1 even if this is 0. So what I'll do is let me just connect that zeros and 1 system. Let me make this VDD. Let me okay, this is what? This is actually D input, no? Okay, let me make, okay, let me apply the clock itself. So what I'll do is let me just take out this supply. Okay, let me use different clocks. Okay, this is A, then this is B, then this is C, then this is D. As long as D is on, you're going to get the output as high. For output to be 0, either AD should be 1 1 or BCD should be 1 1. Let me just run now. So let us see. Okay. So first let us, of course this clock 4 is actually D. As long as this is 0, you can see output is 1. So this will become 0 when D is 1, A is 1. Okay, when A and D are 1 1, you're going to get output as 0. That's what is as per. Of course, if A is 1, if A and D's are on, you're going to get output as 0. This is D, which is 1 here, and this is A, which is 1. For 1 1, output is 0. Again, of course, as long as D is 1, and then B1 as well as C1. You can see here, this one. Here also it is 0. Because D is 1 here, this is C, this is B. So if this and this, all the three are on, you will get the output as 0. So that's how you can be able to verify different combinations here. So this way you can be able to write different layouts using this Microwind structure. So given the layout, first and foremost thing is that you have to write the Euler's path. Euler's path should be such that there should not be any break in the path, so that you can be able to have a single end diffusion for realizing the NMOS transistor, PMOS transistor, and make sure that you have the same gate pattern, input pattern being maintained for both pull-up and pull-down network, so that writing the layout becomes pretty easy. Thank you so much.